So now let's work with linear inequalities. An inequality is a type of mathematical statement that compares two expressions using an inequality sign. So that can be the less than or equal to sign, the greater than or equal to sign, the less than sign, or the greater than sign. An inequality represents a range of values that satisfy the inequality. Since there could be a set of values that satisfy the inequality, we must revise the section on representation of sets under the number patterns module. So everything that I've taught you so far is relevant to what we are going to talk about. So let's just get a general idea of what we're talking about, right? When we work with equations, if I said 2x plus 1 is equal to 3x plus 4, essentially what I'm asking myself when I'm given this type of mathematical statement, an equation, is what x value must I put in here and here such that it will be equivalent on both sides. That's what an equation meant. I need to put in x value here because when I put in x value in here, it'll give me some numerical value. If I put in this exact same x value that I put in here, it'll give me a numerical value, and we want to know, okay, what specific x value will ensure that this two expressions are equal. Now with expressions, what we're essentially doing, when I'm saying 2x plus 1 greater than 3x plus 4, essentially what I'm asking myself is, what x values with the s must I put in here and here such that I can hear numerical values from here that is greater than numerical values from here. Let me repeat that. What x values must I put into this expression and that expression such that I can yield numerical values on this side, on the left hand side, that is greater than numerical values on the right hand side. That's why there's a range of values. Now I will teach you an algebraic methods to solve for that. Right, so what algebraic methods can you use to solve for that without actually thinking of it from the practical standpoint? Because if I have to do it with the way I just said it, then I'll just use trial and error. And I'll run through all of the numbers in the number line, and I'll try to figure out what numbers will satisfy the solution. Right, but the more mechanical and systematic approach would be using maths. But when we start discussing functions, I'll be able to give you the more practical and visual answer to this. That's why functions even lends itself to inequalities. Okay, the set of values that satisfy the inequality is called the solution set. We will introduce the number line, which is the fourth way of representing solution sets. The other three is discussed under the number patterns module. I've already talked about that. A linear inequality is an inequality with the highest degree of 1. You already understand what this terminology means. Highest degree means it has x only and x to the power 0. So x to the power 1 is the highest exponent that will be in the expression, or y to the power 1 or z to the power 1 will be the highest exponent in the expression. When dealing with inequalities, it is important to remember that whenever you are multiplying or dividing by -1, you must reverse the inequality signs. All rules involving equations are applicable to inequalities, like the order of operation rules. So order of operation rules, we're solving for equations. What did we say that we must do with BODMAS or BODMAS? Must follow it from right to left. Okay, but when the only rule that will differ here now is that whenever you multiply or divide by -1, the direction of the inequality sign must change. Let's put this to practice and verify all of the theory that I just talked about now, right? Before we actually delve into linear inequalities, it's very important to understand when we're given a less than, a greater than, a less than or equal to, or greater than or equal to sign, what do they actually mean? Because see, you must always remember this rule, and this must be a foundational rule whenever working with inequalities. The inequality sign always points towards the smaller number. So see, 3 is greater than 2, or 2 is less than 3. Between 2 and 3, which is the smaller number? 2. So it points towards the smaller number. Understood? So in this case here, when you're looking at the first question, you can see, I'm just looking at the first question. This expression here has to be smaller than this expression. This is why I'm saying this must be less than this. But you just remember that it always points towards the smaller number, right? If I have 4 is greater than 2, 5 is less than 10. Understood? And obviously when you start putting variables, then we can say, where is 6x minus 10 less than or equal to 6 minus 2x? Right? Once we have variables, then we can say, okay, where are they equal? But here now, when you're dealing with numbers, you can't actually say equal. They're not equivalent. Numbers cannot be equivalent unless we're dealing with the same number, right? So yes, so that's what I want to say. The foundational rule when dealing with inequalities is that the inequality sign always points towards the smaller number, right? So let's move on with these examples. Solve the following inequalities. 6x minus 10 less than 6 minus 2x. So here we have expression 1 and here we have expression 2. I want to find x values that I must input here and here such that I can output numerical values of this that is less than this. Right, so let's just solve for that. So what would your first step be? So we got 6x minus 10 is less than 6 minus 2x. Okay, so if I add by 2x on both sides, I'll get 8x minus 10 less than 6. And then if I add by 10 on both sides, I'll get 8x less than 16. Therefore, x must be less than 2. So what this means is, think about this logically. What does this mean? Let me draw a number line so you can visualize exactly what I'm saying. Here is 0. Here is 1. Here is 2. Here is a negative infinity. Expand your mind. The number system goes on from negative infinity all the way up to positive infinity. All values from here all the way down will satisfy this mathematical statement. What statement? It will satisfy the statement that this expression here, expression 1, will output numerical values that are less than these ones. Now, why am I saying output? Because if I put in an x value here, it should output some other value. If I put in an x value here, it should output some other value, some numerical value. So, for all values less than 2. So, even if I put 1,9999 recurring, it can go on forever. So, it's not 2. Because at 2, there's some other relationship. We're saying less than 2. Not at 2, less than 2. Even if it's just a fraction to the left of 2. A fraction less than 2 would make this mathematical statement true. Understood? So, let's see, how would we represent this on a number line? To represent the solution on a number line, we'll make use of an open circle to exclude a number, a closed circle to include a number, and a leftward arrowheads to indicate negative and positive infinity. So let's see. I listed a few numbers here. I used the open circle because it did not say x less than or equal to 2. It just said less than. So I'll use an open circle. If I want you to include 2, if they, let's say they had a bar here, then I'll color that circle in. It means I'm including that point. But now I'm excluding it. And it says it's just x less than 2. So any value less than 2. Right? Remember, they didn't say natural, whole, rational, whatever. They're just saying any value, any real value. Right? Because what real values contain? Real numbers contain what? Rational, irrational, integers, whole numbers, natural numbers, and so on. That's what we mean by real. So it can be any value. Whatever the value you like it to be will satisfy this mathematical statement. And we put a leftward pointing arrow to show that we are going all the way to negative infinity. That's the beauty of maths. The logic holds. So you can go all the way down. You can go however far you want to go to the left. It will still make this mathematical statement true. And if you want to do that, put a negative million here, negative million here. You'll see that you'll output a numerical value here that is less than whatever numerical value you output there. Okay. Now, if we use interval notation is using the brackets. Then you'll say SS, which means solution set, is an element of the set what? From negative infinity to 2. But remember, we're not including either of these extremes. And we'll say that the solution set is an element of real numbers. So it exists or it comes from the real numbers. So the value of x can be anything. Can be a fraction. Can be a third. As long as it is a less than 2, it will make this mathematical statement true. Can you see how the number systems are coming in now? Okay. And if you want to use set builder notation, then you'll just say x less than 2, x element of real. So that's set builder notation. So here you have the number line, here you have the interval notation, here you have set builder notation. Right, so the 3 different types of notations that you could possibly represent the solutions that will satisfy an inequality. I'd be very mindful of that. Okay, now you can see I gave a graphical answer. I cannot teach this graphical answer until we've talked about functions, because this will not make sense. So for now, if you want to just take down this notes, or if you can make sense of it, you can. But I want you to just take down this notes, and then when we get to functions, I'll come back and revisit all of the sections and link it to everything that we've talked about thus far. Okay, but for now, don't just take down these explanations, and let's move on to the next question. Okay, let's look at our next question. 3x plus 2 less than 5. So what we are asking ourselves here, before we even start the question, let's understand from a practical standpoint, what are we trying to find? I am trying to find x values that I must input in here so that I can output values, numerical values, that are less than 5. Can you see how simple this is? What x values must I input into this expression so that I can output numerical values that are less than 5? So now if I solve for this, if I subtract by 2 on both sides, I get 3x less than 3. And then if I multiply by 1 over 3 on both sides, I'll get x less than 1. What this means is if I input any x value less than 1, be it a fraction, be it a surd, whatever it may be, any real value less than 1, then I'll have the case where this 3x plus 2 will output numerical values that are less than 5. So from a set builder notation standpoint, I'll say x less than 1, x element of a real, right? From the number line perspective, remember we are not including 1, so therefore it will be an open circle at 1, and then we'll have an arrow pointing towards negative infinity because it means any value less than 1, so any value meaning from negative infinity all the way up. Using interval notation, we will denote the solution set with SS. So SS is the element of open bracket negative infinity is your lower boundary, which is like the very last number, but we can't include it because we haven't got to that point. Your upper boundary will be 1, and then we cannot include 1 because that's what the solution states. And then we'll say the solution set is an element of real numbers. Again, from a graphical standpoint, I cannot explain this yet because we have not discussed functions. So take down this here. If you can understand it, then that's good. If you don't, not to worry. I will explain this when we get to the functions part of the course. Okay, minus 30b greater than 250 plus 20b. What are we asked here? We're trying to find b values that when I input it here and here, I output numerical values in this expression that is greater than the numerical values in this expression at those exact b values that we inputted. So we have to solve for this. We'll subtract by b on both sides, so that will give us minus 50b. That will give us minus 50b greater than 250. And then if we multiply by 1 over negative 50, we'll be able to solve for b. Now it's very important to remember, because I'm multiplying or dividing by a negative, I must change the direction of the inequality sign. So now it'll be b less than minus 5. What does this mean? It means if I input any b value that is less than minus 5, I will output numerical values in this expression that is greater than numerical values in this expression. That's what it means from a practical standpoint. So if you have to express this on a number line, I'll have an open circle at minus 5, and it'll go all the way down to negative infinity, right? For set builder notation, I'll say b less than minus 5, and b is the element of the real number system, right? Or the real number set. And then using interval notation, I'll say solution set is the element of from minus infinity to minus 5, exclude both of the extremes, and the solution set is an element of real numbers. Understood? So these are very straightforward ideas. Okay, now we'll deal with what we call compound inequalities. It takes on this form here where you'll see two inequality signs in the mathematical statement. So how do we deal with these statements? Let's read. We have two types of compound inequalities. When we are given the inequalities in the form of x plus 5 must be greater than 0 but less than or equal to 20, this type of inequality is called a conjunction. Right, here too, we apply the rules to solve linear inequalities. What rules? The rules that we've already explained. The rules that we've already discussed. Right, where if you multiply or divide by negative, you change the direction of the inequality sign and so on. All of those rules still apply. However, we do so for both sides of the inequality. So if I'm subtracting by 5, I subtract by 5 on this side and that side. That's the only thing that you're doing different with the compound inequality. It is important to note that we can express this type of inequality, the conjunction type, in two ways. The first way is shown above, and the second way is as follows. X plus 5 must be greater than 0 and x plus 5 must be less than or equal to 20. See that and? It combines both of these statements. X plus 5 must be greater than 0 and it must be less than or equal to 20. Right? That's the word. This is why the word and is very important, because it has to satisfy both these boundaries. It has to be within both of these boundaries. The word and makes this type of compound inequality a conjunction. So how would you do it? Very, very simple. All you got to do is we're trying to solve for x, so we need to eliminate all of the other constants. How do we do that? Using the additive inverse, as we talked about. So if I have x plus 5, I have to subtract by 5, but where? On both sides. So I'll say 0 minus 5 and 20 minus 5. So therefore x must be greater than minus 5 and less than or equal to 15. Right. So what this means is that values greater than minus 5 to 15 will satisfy this mathematical statement. Understood? So what that means is that if I input, so let's look here, x plus 5 must be greater than 0 and less than or equal to 20. Very, very important. Watch what I am saying. If I input x values in here that are greater than minus 5, so any x value, not including minus 5, greater, any x value that's in between here, from here all the way to here, right? So this is including the 15 as well, including the 15. So from here, any x value here in between here, including the 15, will lie between 0 and 20 and be equal to 20. Understood? So it'll satisfy this mathematical statement. So basically what we're saying is we want to input x values such that we output a numerical value that is greater than 0 but less than or equal to 20. Understood? So if I input an x value and it gives me 20, it satisfied the mathematical statement. If I input an x value and it gives me 0,000000001, meaning that it's just a fraction greater than 0, it satisfied the mathematical statement. Understood? So that's basically what we're doing. We're trying to find x values that I can input in here such that it'll output a numerical value that will be greater than 0 and less than or equal to 20. Understood? So now, so this is the set builder form. X greater than minus 5 and less than or equal to 15, right? And you just have to add in here x element of real. If you draw it on a number line, very simple. What are your two boundaries? Minus 5 and 15. You just have to put in a few numbers here and a few numbers to show a general pattern, but you don't have to list all of them. And then at minus 5, you'll have an open circle because you're excluding that solution. And at 15, you'll have a closed circle because you're including that solution. And then you'll put a line. You'll put a line because you're saying everything, all of these solutions, even if it's a fraction, even if it's a surd, will satisfy this mathematical statement. Understood? Okay, but if I remember, if you're choosing discrete amounts only, then you'll only have dots here. But since all of these other ones, all of these values in between these dots will make the statement true, we do not only use dots, we put a line to show that everything, all of these values in between will satisfy that condition, right? And yeah, you can see here, notice we use the closed circle to include the 15 in the solution set. Using interval notation, we will denote the solution set as SS. So SS is the element of the set minus 5 to 15, excluding minus 5, including 15, and the solution set is the element of real. Very, very important stuff here, right? So that's the three notations: set builder, the number line, and interval notation, right? That's the three ways you can represent this. But I hope that you understand what we are doing. We're trying to input an x value so that it satisfies the mathematical statement that the number that you output here, the numerical number that you output here must be between 0 and 20, but including 20. So it'll be between 0 and 20, but including 20, right? And those values, the solution to that will be that if you take an x value that is between 5 and 15, including 15, will satisfy this mathematical statement, right? So please note the difference in the thinking here. Here you're trying to find out, you got two expressions, you're going to find out where one will be greater than the other, or where one will be less than the other, or where one will be greater than or equal to the other, or where one will be less than or equal to the other. Here you're trying to find out what values you can input here such that you'll output numerical values that will satisfy this mathematical statement, right? Be in between those two values, these two extremes, and whatever. Now, please, this is a topic that we will utilize extensively in the graph and interpretation type questions for functions. So ensure that you have a solid foundation with the section, because these are the things that students don't understand. They don't understand how it fits even in from the graphical standpoint. So that's the reason why I'm showing it to you now. Understood? Now, from a graphical standpoint, this will not make sense until I obviously discuss the function section with you. Right, let's move on to the next type of compound inequality, which is called disjunction. So conjunction, we use the word and. For a disjunction, we're using the word or. The inequality will be written in the form of 3x minus 7 less than minus 4 or 3x minus 7 greater than 8. What are we asked for? We are asked for x values that will satisfy this mathematical statement, or both. Understood? How do you deal with this type? You solve them separately. Very simple. It's as if you're dealing with the two normal inequalities that we've done at the beginning of the video. So solve for this, solve for that, and whatever answers you get, you just write them down. It's a very simple idea, but you're just trying to find out what x values will satisfy this, or both. The word or is very important, because what the word or means, it means it must satisfy either this, or both. Very important when we get to probability. When solving disjunction compound inequalities, we simply want to find a solution set that will satisfy either the first inequality or the second inequality or both. Very important, right? Hence we use the union symbol when we represent the solution set using interval notation. The union is this U, right? Keep that in mind, but the union symbol for now will be the U. Refer to set theory module under the number patterns, but for now you just need to remember that U. So therefore you'll have 3x minus 7 less than minus 4. So 3x is less than 3. So therefore x is less than 1. And 3x minus 7 is greater than 8. 3x greater than 15. X greater than 5. So x greater than 5 and x less than 1 all satisfy this mathematical statement, or both. Okay, so now if I have to represent this on a number line, I'll have an open circle going all the way to minus infinity. And this here will have an open circle here going all the way to positive infinity. And that's how you solve this mathematical statement. So it's a very, very simple one. But you just need to remember, even if you don't understand all of this here, what I meant by here, because sometimes you're still new to the idea, just understand that you're solving each one separately whenever you have the word or. Understood? Yep. And if you have to look at this from a graphical standpoint, you will not understand this for sure. But yeah, if you're looking from interval notation, from the perspective of interval notation, you'll say that the solution set is an element of the numbers from minus infinity to 1, or this means or. When you write this U, it's like a U, like a cup, U, it means or. It can be from 5 to positive infinity. I have already adequately prepared you for graphs and interpretation functions in term 2. I've already adequately prepared you. If you can understand what I wrote here, then you'll understand graph and interpretation will be a walk in the park. But all you got to remember is that this solution or this solution will satisfy this mathematical statement or this mathematical statement or both. That's all you need to remember. So, right, so if I take any, let's take a value like this here. Let's say we took minus half. If I put minus half here, it will satisfy this mathematical statement. But does it satisfy that mathematical statement? No, it won't. It won't, because we're saying in order for us to satisfy that mathematical statement, x has to be greater than 5. So what we are essentially saying is, as long as it satisfies one of the two, it is a solution to this mathematical statement. Let me repeat that. As long as the number satisfies one of these two mathematical statements, it becomes a solution to the mathematical statement. It becomes a solution just because we use the word or. If I use the word and, but I can't use it here, but if I use the word and, it has to satisfy both. It has to satisfy both. Let me repeat that. It has to satisfy both. So that's the reason why it's very important that you understand what the word or means. Or means A, B, or A and B. And means A and B. Strictly A and B. It must satisfy that and that. If I use the word or, it must satisfy either this or that, or both. So if it satisfies both, all well and good. But if it only satisfies one, it still forms part of the solution because we use the word or. That's what the word or means. Either the first, or the second, or both. If it does both, all well and good. If it does not do both, at least it satisfies the first one because we use the word or. But if you have the word and, strictly both must be satisfied. I hope I stressed that point enough. Okay, so let me create a link here. You see, when you're writing your answer using interval notation, this notation seems long. Remember, it is just notation. We use it for communication when we're talking to another mathematician. Understood? So that's all we are talking about. If, let's say, you think the number line approach is something that you can see the answers visually, then when you're writing it like this, keep this at the back of your mind. What is this trying to express? It's trying to express this exact idea. All solutions less than 1, all solutions greater than 1 will satisfy that solution or that solution. I hope I'm stressing this enough. All of these different representations are just ways of showing the exact same thing. It's just different ways of showing the exact same thing. So whatever method resonates with you, right? Let's say that the number line resonates with you. You understand it. You can see what what you're trying to say, you understand exactly what it means. But if they're asking in the paper to use interval notation, keep this at the back of your mind and just use this notation, right? So the solution set is the element of the set from minus infinity to 1 union 5 to positive infinity, and the solution set is the element of the real numbers. This is why when I talk about sets, when I think about sets, I think of it as like a bucket or as a container, and this container has every possible solution in it. So if I have to have a container, if I use this here and if I had a container, it will contain all of these numbers here, even the fractions, even everything, the fractions, the surds, whatever it may be, and all of these numbers here. So if I had to randomly pick a number, randomly pick a digit from that bucket, and I put it in either here or here, it must satisfy at least one of these mathematical statements. Understood? This is what this notation means. Trust me, when we start talking about functions, we are going to use these things extensively, and you understanding this notation is extremely important. And I cannot stress it enough. So this is why you need to understand what we mean by these things. What's the difference between or and and? And I think I've already mentioned this in the algebraic expressions video, grade 9. I'll tell you the difference between or and. So if you're dealing with A or B, it must satisfy either A, either B, or both. But if you're dealing with A and B, it has to satisfy both. Both of it has to be satisfied. Otherwise, you cannot take the solution. Understood? Strictly both. With the or, at least one will do. Right? I hope I stressed this enough. Please, if you have any questions, please message me so that I can stress this idea, so term 2 will be a walk in the park. Right, to really emphasize on this idea, right? So this is a conjunction inequality. The other one that we talked about was a disjunction. Whenever we use the word and, it has to satisfy both statements. So choosing a value of x from this list of possibilities, if I input it into here and I input it into here, it must satisfy both statements. So let's say I take some x value and I put it in here. Let's say I take 1. See, 1 plus 5 is 6. Is 6 greater than 0? Yes, it is. Is 1 plus 5 is 6. Is 6 less than or equal to 20? Yes, it is. So the fact that it satisfies both of these statements, the conjunction inequality, the fact that it satisfies both, therefore we can say that it is a solution. So all of the solutions that are greater than minus 5 but less than or equal to 15 will form part of the solution for this inequality. But if you had the case where we had the word or, then as long as it satisfies at least one of the two, it does form part of the solutions. So that's very important. I hope I created that distinction now between the word and or. Understanding this will become very, very important because this is forming the basis for functions at term 2.